Great. We'll get started. Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. And as part of the Smart Grid series, today's featuring speaker is Dr. Zhaoyu Wang, Northrop Grumman Endowed Associate Professor at Iowa State University. Dr. Wang received the BS and MS degrees in electrical engineering from Shanghai Jiao Tong University, and the master's and PhD degrees in electrical and computer engineering from Georgia Institute of Technology. He is the Northrop Grumman Endowed Associate Professor with Iowa State. His research interests include optimization and data analytics in power distribution systems and microgrids. He was a recipient of the National Science Foundation Career Award, the Outstanding Young Engineer Award from IEEE Power and Energy Society, the Northrop Grumman Endowment College of Engineering Early Achievement in Research Award, and the Harpole-Pentair Young Faculty Award. He is principal investigator for several multi-tool projects funded by NSF, DOE, National Lab, PSERC, and Iowa Economic Authority. He is the TCPC for IEEE Power System Operation, Planning and Economics Committee, the chair of PSOPE Award Subcommittee, and the vice chair of IEEE Distribution System Operation and Planning Subcommittee. He has served as an associate editor of IEEE Transactions on Power Systems, IEEE Transactions Smart Grid, IEEE Open Access Journal of Power and Energy, and IEEE Transaction on Sustainable Energy. That's quite a mouthful. Thank you so much, Dr. Wang, for joining us as part of the webinar series. It's a great honor to have you as part of the webinar series, and I appreciate spending your time this morning with us. The floor is yours. You can share your screen.
Yeah, let me share my screen. So let me go to Zoom and share. Give me 1 second. Can you see it?
Yes, yes.
Okay, pretty nice. So let's go to the full screen. So is it good?
Yes, thank you.
Okay, thank you. And thank you, Prakash, for your very kind introduction and for the invitation. And I feel very honored to present our work in this webinar series. Like Prakash mentioned, my name is Zhaoyu Wang. I'm currently working at Iowa State University. So today I will talk about some data analytic work that we have done in power distribution systems. The reason I select this topic because firstly, this is a AI cybersecurity theme. And I didn't do anything on cybersecurity, so I'm thinking that maybe I can present something on big data that's still relevant to the main theme of this webinar series. Another big reason is that so this is not purely research. So what I will present, a lot of them are about the industry collaborations and the industry standard and the implementations. So I would like to just let you know, we're not only doing theoretical research, but also generating impact to the power industry. So firstly, just a brief overview of power system. I think most of audience know that we have the generation part, we have transmission part, and goes to the sub-transmission part, and then go to the distribution part. So distribution part is our focus today, and anything below 35 kV is considered the distribution system in the United States. And certainly it has a primary, we call it a medium voltage feeder. It could be 35 kV, it could be 13 kV, it could be maybe as low as 2 kV for some very old system. And we call this a primary feeder. And we also have the secondary, you can call it network, but I would not say it's a network. It's more like a radio, a star-like drop lines. So we call it secondary system. In European countries, they call it a low voltage system. So this part is after this distribution transformer, it goes to 120 and 240 volts. So that's what the distribution system is. So where the data is, so I would like to say there are multiple places that we have data. We have SCADA data. Usually it measures the feeder head and some middle points of the feeder, but most likely it's a feeder head, measures PQ and V, and also current. Another thing is a smart meter. That's a lot of utilities have smart meters nowadays in the US. That's installed at your house, measuring the energy consumption and the voltage at your house. Most utilities only measure energy and voltage. Some utilities are unable measuring the reactive power. So it depends on the utility setting. So SCADA system can be as fast as let's say maybe a few seconds a point, and the smart meter is usually 15 minutes for the sampling rate, and could be half an hour, could be hourly sampling rate, depending on utility settings. And there's some recently there's some advanced sensors like micro PMUs also in the distribution system, but they are not widely deployed. We have a project that deploying the very first a few sites of micro PMU here in the state of Iowa with Atlanta Energy. And micro PMU, the sampling rate is similar as traditional PMU in transmission system is about like 120 points per second, something like that. But I cannot do point on the wave. You can see that it's basically sampling 2 points per cycle. So it's still too slow if you want to do point on the wave. So this guy usually come with another sensor called P-Cube, which can do power quality, waveform sensing. That's much faster than micro PMU. So anyways, I just want to give you a brief overview of what's distribution system, where they are. They're closest to the customers, to ourselves, and what are the commonly seen sensors and their sampling rates, and what they are sampling in distribution systems. And I list a few utilities name. The reason I list them because those utilities we have the data, like Atlanta Energy, like I said, we have the micro PMU data. We also have smart meter and other data, but smart meters, we have all these other utilities in Iowa that providing all the data and also system models to us. So the research is based on the real data, not the synthetic or simulation data. And so what I will talk about today are two topics. There are so many applications of big data techniques. Okay, so we will basically talk about two of them. One is a conservation, voltage reduction assessment, and field results. There's no AI in this subtopic. But it's quite industry focused. You will see how we use data to help industry to evaluate conservation voltage reduction effect. Basically, you want to evaluate by reducing a certain amount of voltage, how much energy has been saved. So that's what we will do. And we will use SCADA data to do that. And to find the low to voltage sensitivity so that you can find by reducing certain amount of voltage, what's a load reduction. And another subtopic is voltage estimation in the secondary distribution grids. Secondary, like I mentioned, is here, the low voltage network passing this distribution transformer. You go to the low voltage part. Those part are, even for utilities, most utilities don't model that because they're too detailed. And not much interest in the past because these are just a few job plans, star-like job plans, very short job plans, but now it's it's getting more attention because of the integration of DERs. So where's the DER? DER is here, right? So need to go to the job plan and then go back to the distribution transformer and then go to the primary feeder. So because of the integration of this renewable energy, it got more attention now. So we will try to estimate the voltage in the secondary distribution grid using smart meter data. So basically, this use voltage to load sensitivity. That means by injecting certain amount of power, P and Q, what's the impact on the voltage? So those are the two topics we will cover today. And firstly, let's go to the CVR. So what's CVR? Some of you know that, many of you may not know that. It's actually a very commonly used industry practice. It's an energy efficiency, a practice that reduces the energy consumption by reducing feeder level voltage. So what does that mean? That means I change the substation load tap changer. I reduce it, I change the tap and reduce the voltage at the substation a little bit. Certainly, you want to make sure your end of line voltage or everywhere in your feeder, the voltage should still within the standard. Probably you know the ANSI standard 120 plus minus 5%. So every customer still receive this standard voltage, but it's at the lower part of this range, 120 plus minus 5%. Instead of running the system at the higher part, we run it at the lower part. Okay, this won't have any impact on customers. Ideally, it won't have any impact on customers. You won't feel that. And utilities won't need customers' permission to do this. So that's why utility like it. And it's super easy to implement because you only need to coordinate the LTC and the voltage regulator to reduce your system voltage. So a major benefit, like I said, is non-intrusive for sure, and no much impact on the customer either. So, but the question is that how much energy I have saved by reducing the voltage. We use this measure, CVR factor, conservation voltage reduction factor. So it's pretty easy to understand. You reduce certain amount of voltage and you save a certain amount of energy. So the ratio between the two is a CVR factor. If you have higher CVR factor, that means your system, is good for CVR, right? If you have very low CVR factor, that means your system is not very good candidate. CVR factor can be negative. Negative means if you reduce the voltage, the energy consumption goes up. That could happen. And that means this is really, we should not do CVR on this feeder. But the question is that I don't know what's delta E. Why I don't know what's delta E? If you look at this figure, you will see it very clearly. Okay, so this blue line showing you the measurements, let's say probably at the feeder head, what's the active power at the feeder head. You can see this is a CVR off period, okay? And then we start voltage reduction by certain amount like this. Reduce voltage a little bit, and then the consumption should go down and go up, just following the normal trend of a load profile. And then we resume the voltage to the regular voltage level. The consumption will go to the regular profile. So the blue line is something you measured at the feeder head. But my interest is what's the red dotted line. That means if I didn't reduce this voltage, what the consumption would be, right? If I didn't do that, what the consumption would be. If I know this red dotted line, the difference between the red dotted line and the blue line, the area is marked as green here, is a delta E, right? That's very easy to understand. But the question is that how do I know this red dotted line? I will never be able to measure it for sure, because I can only apply 1 voltage to the feeder. I can't apply 2 voltage to the feeder at the same time, right? So basically you will never know what would happen if you didn't do this. So the question now is become how can we estimate this red dotted line? So that's how we use the SCADA data to do that. So that's just give you some background of CVR. So what I will present next is actually a lot of contents coming from this draft standard P3102. It's an IEEE standard initiated by ComEd, and we have a task force under the TND committee to really drive this standard. And I'm serving as a secretary for this task force. So if you are familiar with the IEEE standard, you know how difficult to get it done. We've been working on this standard for almost 4 years. I think it's a little over 4 years already. So we passed 3 rounds of ballots. So everybody votes, and this ballot include people coming from the industry, academia, national lab, vendors. All of this need to vote. And you need to have certain amount of approval rate before going to the next step. And our approval rate is 96, so certainly qualify for that. But another thing is that for each round, you will receive some comments from the reviewers asking you questions. For example, for the first round, we receive 100 comments, over 100 comments. So I'm pretty detailed. And you must address all of them. And for the second round, if you still have comments, you still need to address. So this process continues until there's 0 comment from the balloting group. So we already passed 3 rounds. Now we have 0 comment. So that means we can submit this standard to IEEE RevCom to review and approve. So if we're successful, we are able to publish this standard as a just official IEEE standard probably in fall semester. So that's a big achievement because all the industry will follow this standard to evaluate their CVR effect. And so I would like to mention that how do we calculate CVR factor? Basically, how do we estimate that red dotted line, right? What would happen if I didn't apply voltage reduction? So the first method is we call it a comparison-based method. It's a very simple one. You select 2 similar feeders in the same performance period, apply voltage reduction on one feeder and the regular voltage on the other feeder, and you calculate the difference in the power consumption. Another one is you select one feeder and apply voltage, normal voltage to the feeder, and then apply the reduced voltage to the feeder for another amount of time, and then you do the you calculate difference in the consumption. But you can easily find the problem with this method is that there's no 2 feeders that are exactly the same, right? So your basic assumption here is that you assume those 2 feeders are exactly the same. Then you can do the comparison, but actually you're compare apple with orange, similarly to the other method. So it doesn't work very well. Even for one feeder, the same feeder, for different time, the feeders loading is different. You can't just compare them. So that's not a good approach. Another method is a regression-based method. This is very commonly used by a lot of utilities here in the United States to evaluate their CVR factor. So it's actually pretty simple. It's like load forecasting. They model the load as a function of temperature and also as a function of CVR on and off. And then they try to use the just a normal voltage data to do the regression so that okay, how this load is correlated with voltage and with the temperature and also with CVR status. And after that, when you have a new set of temperature and CVR status, you will be able to just reconstruct that red dotted line. So basically, if we go back, so those 2 methods are just using different ways to help you estimate this red dotted line. Either select a control group or using the just very simple linear regression method to do that. It's like a load forecasting. You estimate this red dotted line, and then because this blue line is measured anyway, the difference between the 2 is easy to get if you can successfully estimate this red dotted line, right? So, but you can find the problem with this method as well. Certainly, the load is not only as a function of temperature, and also it's not a linear function of temperature either. But this is an easiest way to estimate the red dotted line and getting the CVR factor. So it's still commonly used by the industry, but we can easily understand the problems or the drawbacks of this method. So then another method actually, this is actually proposed by us, and it's included in that IEEE standard as a standard method as well. We call it load modeling based method. So what does that mean? That means the nature of CVR is that load are sensitive to voltage, right? So that's, I mean, if the load is not sensitive to voltage, when you reduce the voltage, what would happen? Let's consider extreme case. All the load are constant power load. When you reduce the voltage, what would happen? Your total consumption will go up. You know why? Because their constant constant power load, when you reduce the voltage, their current will go up. Their current go up, that means your line loss and the transformer loss will go up. So the total consumption of the whole feeder will go up. So you will have negative CVR factor in this case. So didn't save anything. And let's consider another extreme case. All the load are just a resistive load, purely resistors. So in this case, when you reduce the voltage, you will have the maximum amount of load reduction, right? So, but in practice, you won't have either case. So you will have a mix of constant power load, constant impedance load, and constant current load. So you will have a mix of them. And this mixture is changing with time depending on the load composition, depending on every one of us switching on this device, switching off that device. So in total, when you look at this feeder, as a feeder head, you will say, okay, the load composition, the composition of constant power part, constant impedance part, and constant current part are changing with time because customers are switching on and off their devices, right? So the load modeling method is trying to model the load as a function of voltage and other factors, and then try to capture the load to voltage sensitivities by identifying the model parameters using the data. So let's see how we model the load. We model the load as a ZIP load. It's commonly used by the industry. So what's the ZIP load? It's basically you model the power consumption as a function of constant impedance part. Why this is constant impedance part? Because it's 2 voltage square. You model the load also as a composition of constant current part, and also the constant power part, which is insensitive to the voltage. And this alpha, beta, gamma representing the percentage or the composition of each part, constant impedance part, constant current part, and constant power part. So this is a very simple model and has been used by industry for many decades. So that's why we select this model to model the load to voltage sensitivity. So for example, if I set alpha and beta to be 0, both are 0, what would happen? That goes to the extreme case that all the load are constant power. You will see negative CVR factor. If I set beta and gamma to be 0, and that goes to the other extreme case, all the load are constant impedance, you will have the maximum CVR factor, right? So but in practice, this alpha, beta, gamma need to be identified from the data. We call this load identification, load model identification. And also alpha, beta, gamma, as you imagine, they are changing with time, right? So that's easy to understand because you keep switching on and off your devices and nobody can control that. So they should be changing with time, maybe changing slowly, but they're still changing, right? So how do we do the load modeling identification or load identification? So we call this to identify the time varying load parameters, alpha, beta, gamma. I put index I that's representing the time, okay? Basically the sampling point. And a general optimization can be formed as like this. So what's this? This is a model, ZIP model, right? You want to identify alpha, beta, and gamma. This is a measurements. I only talk about active power part. You can do similar thing for reactive power part, but we rarely do that. You know why? Because utilities are not interested in reactive power saving because they're not billing you for that. So they are more interested in active power saving. So that's why we focus on active power part. And certainly alpha, beta, gamma should be between 0 and 1 because in total alpha plus beta plus gamma should be 100%, right? But this alpha, beta, gamma are changing with time. That's why it has the index I, and we want to identify that in real time. So what this optimization objective telling us is that this model, you try to fine tune alpha, beta, gamma, find the combination of alpha, beta, gamma in real time, so that this model tracks your, I would say your measured active power. So that's easy to understand, right? If your model tracks your measured active power, you assume this model, can fit your data or can represent your load behavior. So that's the basic idea. And how do we solve this? Well, the objective function is convex with respect to coefficient, so you can simply just take first order gradient to them, and then you will find a matrix like this. So to solve this alpha, beta, gamma, you need at least 3 points, 3 measurement points to solve that. Otherwise, you won't be able to do the inverse, right? So you have, so that's why the below problem has a unique solution if you have 3 measurement points at least. And so that's why we have this sliding window method. Okay, in each window there are 3 data points. But sometimes if 2 data points are very close to each other, you will still make this problem singular, and then we have to probably include this fourth data point or fifth data point. So this time window is also changing depending on how different the measurements are. But at least we need 3 data points, right? To solve this equation. And this is not the only thing we do. Another thing we need to do is that we need to deal with a constraint. So we haven't dealt with a constraint, and we also need to improve the robustness of the load. So we propose a method called over-determined least square optimization using the soft constraint like this. So the first half part is just a matrix you have seen before. That's easy to understand. Basically, you take out the first order derivative, you will find that. And but the lower half part, these 3 rows, actually we call it a soft constraint. So why we need that? So we do this because if you didn't do that, when you apply this method to the real data, you'll find a big jump up and down, spike up, spike down of all these alpha, beta, gamma identified parameters. So that means your identification is not stable. To stabilize that, we need to add this. So this means the solution of the initial estimation is a weighted average of 2 components. One is the solution of the current time window, alpha, beta, gamma, obtained by solving the original optimization problem. So that's this problem. Okay, by solving this problem using the current 3 points in that time window. I mean 3 measurement points in that time window. By the way, we only need power, IQ power, and the voltage measurements. Okay, P and V. So and then the solution from the last time window is also here. So basically, it's more like a forgetting factor. So your current solution is your solution is based on the combination of your current estimation and your previous estimation. So that this parameter won't jump up and jump down too sharply. Okay, so to stabilize this identification process. And anyway, I'll skip all the details, but you can get a feeling after solving this matrix. You can find alpha, beta, gamma for each time window. And remember, each time window has at least 3 measurement points. Measurement points means active power and voltage at the feeder height, okay, at the substation level. Because we are not interested in each customer's CVR factor. We are only interested in substation or feeder level CVR factor. That's what the utility will report to the regulation agency. And okay, another thing, suppose you have alpha, beta, gamma. The next thing we need to do is that we need to calculate delta V. We also have delta V. That's easy to understand. Okay, because voltage didn't change too much, didn't fluctuate too much. So basically you use the average of your normal voltage and the average of your reduced voltage. The difference between the two, we call it delta V. So that's still an estimation, but it's not a bad estimation because voltage profile didn't fluctuate too much in distribution system. And so if you have delta V, you can go from the original definition of CVR factor is here and do some derivations. Eventually, you will have this equation. Let's look at this equation. CVR factor equal to this equation, and you have alpha, you have beta, you have gamma, which were identified before, right? Using that method. And you have delta V, which were estimated just here, very easy to estimate. And then basically you have everything in this equation. And then you can calculate several factor for this time window. Right. So that shows you how we use this identify alpha, beta, gamma to calculate several factor. And but this several factor, you can see that it's only it's time varying. For each time window, you will have a several factor. That's why it has the index I. For each time window, you have that. So that's actually not what the utilities wants, but that's true. Okay, for each time window you have it, that's true because your load composition changing with time, and your several factor should change with time. The problem is that when utility report CVR performance to the regulation agency, they want to report just one single number. So that we need to we can't report them every three, let's say every 3 minutes what the CVR factor is. The regulation agency won't be able to understand that. So we need to combine them to be a single CVR factor. How to do that? It's very easy to do. So suppose your CVR factor is estimated here, right? It's estimated here. And suppose it's correct. By using this equation, you can reconstruct the load profile because this P on is measured. Delta V, you calculate that. Several factor, you identify that. So you have everything in this equation. You can estimate what would happen if I didn't have this voltage, what the load consumption is. So that's P off estimate. And use this equation. I'll skip the details, but you can basically reconstruct this red dotted line and the difference between the red and the measured one using this equation will give you the delta E. Will give you the delta E, and then you can calculate several factor. That's one single one because you have delta E and delta V, just one single several factor. So basically, you combine all this, convert all this time variance several factor to be one single one. And then you can report this to the regulation agency. So here give you some case studies that we have done using the real data. One is we have done two data sets, okay? Both are measured a long time ago in 2016. And the one is D2 data set, the other is D3 data set, have 5 different resolutions from 5 minutes to 60 minutes. We want to test the robustness to the data resolution. And both the data sets have CVR on and off test. In D2, this is D2, you can see CVR is applied, voltage reduction is applied during this time, about 1 week, and another week. It shows here, you can clearly see the voltage drops here and drops here. In other places, it's just a normal voltage, okay? And this is active power, this is a temperature measurements. And in another data set, D3, you can see we do CVR on and off every other day. So that's why you see voltage profile like this. Every other day, you have reduced voltage. And then you have active power, you have temperature measurements. Why you need temperature? Because we want to compare the regression-based method. Regression-based method need temperature, if you still remember that. It models the load as a linear function of temperature, right? So we consider two cases. Case one, base case, just clean data. And case B is that we analyzing some missing data. So we just randomly remove some certain amount of data to see the robustness of different method. And here shows you the results. So you can see for comparison-based method, regression method, and load modeling method for each data set, what's the energy saving and what's the CVR factor. This is there's no missing data here. Okay, it's just a complete data set we applied here. One thing you can easily observe is that for D2, this data set, actually CVR factor is calculated everywhere, right? From negative to positive 3 to positive 0.8 or around 1. So which one is correct? Honestly, it's hard to say because you will never know what would happen if there's no voltage reduction. So it's hard to say which one is correct, but one thing I can say that certainly negative is wrong. Reason is that we carefully select the feeder, so this feeder won't have negative CVR factor. Okay, it's not an industry feeder, it's a residential feeder, so it must have positive CVR factor. And another thing is that 3 seem to be very high, which is not possible. CVR factor should be around 1, based on our experience. So I'm not saying this is exactly correct, but this is I would say closer to the truth. And for the other data set, D3, we have much better result. And we see this CVR factor is fairly consistent, so they could give us some confidence that this D3 data set for this feeder, for all 3 different methods, you have a relatively consistent CVR factor, should be around 0.8 to 0.9. So that's the CVR factor for this feeder. So another test case, we test under different missing data, different level missing data. What are the CVR factor? You can see that for the comparison-based method, it's not surprising. It give you results everywhere. Just saying it's not stable. It won't be stable because this method, I told you, you're comparing orange with apple, right? So it won't give you stable results at all. And the regression-based method is fairly stable, but still at a very high end, around 3, which is seems not realistic. And load modeling method give you a very consistent result and within our normal range around 1. And also this case B is on D3, but will still give you 5% to 30% missing data. You can see how the CVR factor calculated. Again, for this data set, it's fairly consistent, giving us some confidence that CVR factor should be around 0.8 to 0.9 for this feeder. Okay, so what's the conclusion for this part of study? So one thing you need to understand is what's the significance of this. So many utilities are required to report this CVR factor to the regulation agency every year. Why? Because you claim to the regulation agency that you save certain amount of energy. They need to audit you. So that's why they need this CVR factor. And that's why that IEEE standard matters, because we need to have a standard way to quantify this CVR factor, right? Otherwise, how can I audit you? So that's why it has a lot of industry impact, and many utilities are very interested in that. But I told you this is a complicated problem because you will never know. The problem is that there's no ground truth. You will never know what would happen if I didn't do this in the feeder, right? So all these methods are estimations. I have to admit, all of them are estimations, hard to verify their correctness. But based on experience, you can get a feeling, okay, which method give you closer to truth estimation, which method give you which I would say impossible results like this one, right? It certainly is impossible to give you the results everywhere. So just showing you this method is not stable at all. Okay, that concludes the CVR part. Let's go to another part, which is more research-oriented, actually. This part is to estimate the secondary network voltage. Before I move to the secondary network voltage estimation, I would like to just mention why this is needed. So I know we are close to the timeline, but I'll go this very quickly. So I can tell you this is part of a project that's trying to do the data-driven hosting capacity, solar hosting capacity estimation. So when you do the solar hosting capacity, it's constrained by 2 things. One is the voltage. So you can't, when you install the solar, you ask permission from the utilities. They will do a study. They will say, okay, after you install the solar, what's the impact on your voltage? Will that cause a lot of fluctuation in your voltage? If so, probably that's not good, right? So, and the other is a thermal constraint. It's basically if you push back power, will that exceed the capacity of your distribution transformer? So we call it thermal constraint. So this voltage constraint is actually what we are focusing on in this subtopic. We're trying to use a data-driven method to estimate the voltage constraint. So what does data-driven mean? Data-driven means how do I estimate voltage? I can do power flow, right? If I have the system models, I model the system. I can run different scenarios of the power injections from the solar and the load, right? The net load, solar load minus solar is a net load. I can just run different net load scenarios using power flow, and then I know the voltage. Then I can see if there's any voltage variation and how much that variation and how frequent that variation could be. So that's a model-based method. So what's the problem with that? The problem with that is that you rely on the model. It's time consuming and rely on the accuracy of that model as well. So we can see we want to understand whether we can do this in a data-driven manner. That means we only use smart meter data. We do not run power flow. We only use smart meter data, and we do not know the topology of your system, but we can still estimate the voltage and based on different power injections. So that's the main purpose of this motivation of this research. Okay, so some motivations you can see. Just want to let you know that this is not a new topic. A lot of people have done this. Okay, trying to use smart meter data to train a neural network and then to estimate the voltage in the distribution system under different power injections scenarios. So many people have done that, but the problem is that existing work overlook the low voltage secondary distribution networks. They only model the primary side, but secondary side is important because your solar is connected to secondary side. And also they're performing poorly for the high impact, low probability extreme case. That means if the neural network, if you encounter some unseen scenarios, the neural network didn't perform very well, and also lacking the physics informed interpretability. So we propose a model-free voltage calculation for integrated primary secondary network based on the physics-inspired neural network we call PIAN, using only smart meter data. How we do this? If you look at this figure, you can see this still the primary line, okay, and each dot represent a distribution transformer. If you look at this dot, under this dot, there's a distribution transformer, and under this distribution transformer, you have certain houses. Some of them may have solar panels, right? So the question is that under different solar injections scenarios, because you're doing planning, okay? So it's not like they already have solar. So what if I want to install solar here? So then you will have a lot of different solar injection scenarios for this guy, right? But what I want to know is that under different solar injection scenarios, what are the voltage of this part? So that's an estimation, right? So you can run power flow to do that, but like I said, we want to do it in a model-free way. So how do we do that? We actually use this equation, okay? Use this equation. You can see that voltage, this is a linearized power flow equation. Voltage is modeled as a function of customer active power and reactive power injection. Okay, and this is this part, and the other part is consider the voltage variation at the primary side, at this side, because this voltage will also affect voltage here, right? So you need another component to capture that part. And the last part is to compensate for the linearization error, because you do a linearization, but line and the secondary transformer losses, they are actually not linearized. So there must be some linearization error. So use this part to compensate for that. So what I will do next is that I have this P, Q, and V mirrored as smart meters. I will try to use neural network to capture this equation. So that's what I will do next. That's why I call it physics-informed neural network. If you look at this, you will find it, okay? You have a lot of neural network, and each neural network represent is trying to capture each part of this equation. For example, this part is trying to capture the linearized power flow, and this part is trying to capture the the impact at the primary lines voltage, and this part just sorry, this part actually captures the multivariance as a primary side, and this part captures just the linearization error. Okay, so and by using a lot of historical data, PQ and V, to train this neural network, ideally you will be able, this neural network should be able to replicate the behavior of these physical equations, right? So that's what we are trying to do now. And I can show you some case studies. So we consider 5 scenarios for this two system. One is an APRI 12-bus system. The other is a real 40-bus system coming from Iowa utilities. Okay, so we have smart meters for all of them, and we do the training. Scenario 1, scenario 3, scenario 4, scenario 5, they're basic training scenario. What does that mean? That means there's no solar penetration in the training side. And but scenario 2, we gave a 25% solar penetration just randomly. And we do the testing. Testing, sometimes we use basic, sometimes we use just a different penetration level of solar or EVs. And so let's go to next. So and then I show you the results. Show the results you can see for different system, APRI 12 bus, Real 40 bus, and APRI Circuit 5. For different scenarios, what are the performance of voltage estimation for different method? There are physics-informed neural network. There's a linear neural network which does not have the compensation part, this part or this part. It's just this part. We call it linearized neural network. And there's a DNN, which does not have any physical information. You just throw in PQV, and then it gives you PQV out. So it's purely black box. So we consider these 3 cases, and you can see that. Let's look at this. You can see, okay, for the voltage estimation error, certainly if you use black box model, it will give you a lot of error, right? Under different scenarios. But if you use a little bit of physics information, like this linearized neural network, the error has been significantly reduced. If you use a lot of physics information by adding this compensation part, linearization error compensation part, and also considering the variance at the primary transformer voltage, primary side voltage variance. So we'll have much better results like this blue result. That's a PNN model we propose. Okay, similarly for other test cases. And another thing I want to bring your attention is that you can see that for different scenarios, their error are also different. So what does that mean? Why S5 give you the highest error? Because S5, you train the system using very basic scenario. There's minimum solar penetration. But when you do the testing, when you do the validation or testing, you have you put a lot of solar penetration there. So that means this neural network haven't seen such a high penetration level in the training data. So we call this extrapolation capability. So the test the neural network's capability to test the neural network's performance under unseen scenarios. So that's very important for solar hosting capacity analysis, because what you have seen is the past scenarios, and what you're trying to predict is the future scenarios. And we know that solar will increase. So your training data will have much lower solar penetration, but you want to predict the future with a much higher penetration. So the extrapolation capability is very important. And it shows you that if you just use black box model, DNN, throw in a bunch of data, and then get out the voltage, you won't have much extrapolation capability. But with a physics-informed model, you will have much better extrapolation capability. So that's a main point of combining some physics information into this neural network training. And that's about the research presentation. Before I conclude my presentation, I want to show you some data sets that I think I shared this many years ago. This is a real system in the state of Iowa is coming from Iowa utility. I can't disclose which utility it is, but everything in this feeder is real. It's not synthetic. Okay, it has 3 feeders, 1,120 customers. We provide all the specifications of all these lines and transformers and other equipment, and we also provide the 1-year smart meter data. They are also real for all these customers, so that you can use that as a real test case for your algorithm. So I'll conclude my presentation. So we present 2 parts. One is a CVR performance assessment, trying to understand, okay, how much voltage, how much energy has been saved by reducing certain amount of voltage. And we use SCADA data. Actually, feeder has SCADA data to do that. And we show you different method, comparison method, regression method, load modeling method, and show you different performance under different scenarios. And another thing that we have done is that we showing you using the smart meter data, trying to estimate the secondary voltage in the distribution system. So it's important because by doing this, you can estimate, okay, solar hosting capacity by injecting certain amount of solar, what the voltage would be. So use neural network to capture that part. So I think that's all for my presentation, and I welcome any questions. Thank you.
Thank you so much, Dr. Zhao, for a great presentation. I think, first of all, kudos to that IEEE standard, effort. It's a 96% approval with 100 comments, addressing all those things. It's a big task.
Yeah, we spend a lot of time on that.
So I think that's a great effort. We can take questions now. Maybe I'll start with a couple of questions. And like you already pointed out that due to this regulation, utilities are looking at, they have to do this CVR for cost savings and energy efficiency. Where are we right now from you talking to these utilities and industries in terms of, do we have those infrastructures in place to implement CVR, or to, if so, how frequently they should be doing the CVR? As you mentioned, there's no ground truth available. So how do you see moving forward in the enforcement of CVR? And I know I kind of loaded that question in a bit, but the big questions: do we have significant infrastructure to measure these uncertain voltage sensitivities that you talked about?
Okay, that's a good question. Actually, I can tell you where we are at the CVR. From the implementation point of view, most utility already have that. So that's why utility like this method, because they don't have to invest too much. It's not like demand response that you have to establish these communications. You have to obtain the consent from the customers to do this, right? You have to recruit customers. So all these are big efforts to utilities, but this CVR is different, okay? As long as you have LTC at your substation, utilities certainly have that. And then you can just lower down that, change your tap positions. Then you can lower down the voltage. Of course, you can do it in a much fancy way, more fancy way, like, okay, I measure certain points of the system, and then I do this automatically. I just program it, and then I can lower down the type a little bit, but still make sure the voltage in the system within the range. And when the loading condition change, I change the type according to the loading condition, and I coordinate all the voltage regulator in the system. I can do that automatically using the ADMS if you have that capability. But many utility don't even have to do that. You can do that manually. You just lower down the voltage a little bit. Probably you won't get a lot of voltage reduction because you try to be very conservative, right? You can't lower down that feeder high voltage too much, because the end of line voltage will drop too much and will exceed the range if you didn't have feedback loop. But you still have something, right? You can be very conservative. Instead of lowering 5%, I only lower 1%. I still get some energy saving. So in terms of the equipment to do this, utilities already have that, and that's why they're ready and they want to use this method because it's simple, easy, and almost zero cost. But in terms of measurements, I think utilities are also ready because you just need SCADA measurements as a feeder head. Most utilities have that. Some small utilities in Iowa, they don't have SCADA. So that's another story. But most utilities, they have SCADA as a feeder head to measure the active reactive power and voltage. So no matter which method you use to calculate CVR factor, you only need active power, reactive power, and the voltage. Probably you don't even need the reactive power. So they are already reported by the SCADA system. So that part is not a concern either. And but I got your question is that okay, since there's no ground truth, is there anything we can do to improve this to validate this result or to improve this assessment? Honestly, not much we can do because it is what it is. You can't apply two voltage to the same feeder at the same time. But one thing you probably could do is that you can do simulation. Because in simulation you can have a fully controlled loading condition, right? So I do voltage reduce the simulation once, and I make sure the loading condition didn't change and do the normal voltage simulation again, and then the difference between the two will tell you the CVR factor. But remember your simulation based on the models, so your model may not be true, may not reflect the practical system. So I would trust the measurements more than the models, because model certainly we know there are accuracy problems and mismatch problems, cannot reflect the practical system. So anyway, currently the most utility they just use that regression method I mentioned, just simple regression method to report their CVR factor to the regulation agency. So from this standard, we're trying to tell utilities, okay, there are multiple methods and you can apply, often maybe, and then compare the results that give you more confidence when you report your CVR factor to the regulation agencies. Yeah.
Thank you. The another question is, how realistic is this CVR? And as we see this, more penetrations of EVs and
Yeah,
solar
good question. Very good question.
distribution, right? And especially maybe this pin method, is maybe something ideal to look into, something like more AI-based. Do you see any, how can we improve the accuracy of whatever the CVR, quantification is much more, real-time situational. Yeah.
That's a very good question because actually that's a question some reviewer ask us in the standard preparation. Currently, what we are doing is that we need to remove that DER part. So because that's really mess up the calculation. Because they say if you have DER, you have solar, your energy consumption measured as a feeder head will be lower anyway, right? Because you have solar to compensate for your loading, customer load. But that's not due to the CVR, that's due to the solar. So, and most utilities, they don't have any measurements of all this solar because they're customer owned. So it's hard to quantify their impact on the CVR unless we have accurate, solar output measurements from all the solar in the feeder. Then we remove that part. Then we do the analysis purely on the net load. Then we can find the true CVR effect. Otherwise, it will be combined by the both CVR saving and the solar saving. So hard to remove that part. So what I have shown you, those feeders, they don't have DERs. We do the analysis. So if we do have DERs, we need to figure out how we remove the DERs impact that will mess up the calculation that I showed you. That's true. I don't have a solid answer now, but what I can imagine is that I just need to remove that impact by removing their finding the true net load. But it's hard for utility to do that. It's easy for researchers to do that in simulation, but it's hard for utilities in practice because they don't have measurements of the solar.
Thank you. Thank you. I just want to hear your perspective on this. Thank you so
Yes.
much. Let me read some question. Okay, what are your plans to test CVR model in industry with industry partners? That especially the loading method that you talked about, is
Yeah.
that deployed?
That's tested. Well, I show you the test cases. Those test cases are already tested using the real data. So it's already in the standard. So it has already been tested using the industry data. And we're working with multiple utilities. I don't want to disclose their name, but we're working with at least 3 utilities now to apply this method in their CVR analysis.
All these are non-intrusive calculations, right? Right now, the CVR.
Oh, yeah, you don't have to install anything. So it's just because you're not interested in customers CVR saving. You're only interested in the whole feeder saving. So you only
Sure.
need feeder head measurements, right?
But how frequent do you need to compute the CVR or look into this?
It depends on your measurement resolutions and because most of SCADA is pretty fast actually. Many SCADA are pretty fast. You can do it just based on the SCADA's resolution. Theoretically, this CVR factor shouldn't change too much along the time because we're talking about energy effect, right? So, and it's a relatively longer time compared to the transient or dynamics. So it's not that time frame. So you just use SCADA system, that's good enough.
Does the DLR, dynamic line rating, affects such CVR
If
computation?
CVR is it's on distribution system, so there's
Okay,
no dynamic line rating in distribution system.
okay,
Yeah.
good. Let's see. Okay, thank you for the presentation. I would like to ask, since there are developments for AI-based chips, do you think for future sensor standards should be enforced to collaborate with AI-based chips for data filtering or pre-analysis for in the context of grid ecosystems for maybe some real-time?
Yeah, I'm not very familiar with AI chips, and I think what you're asking is more about is there should there be anything for just AI chips specialized for the power grid
I
application?
think that the question, the way I understand, probably that these data-driven algorithm needs to run on something, in terms of
Yes.
real-time learning. If they want to, or maybe we are not there yet. Maybe that's something
Uh,
it may not be even needed, or maybe.
uh, yeah. So I don't have a good answer for that question, but I just feel that so we're far from that in the industry practice. AI is still not not I would say not broadly applied in power industry. So that's why when I was invited for this webinar, I was thinking a lot. I was thinking, okay, what I should do. So we can present some work using AI to do the control, using AI to do the voltage control, service restoration, microgrid control. We have all this kind of work. But I can tell you that utilities won't use that, right?
Yes.
But currently, what is more acceptable to utilities is using the big data analytics. It's still AI, right? It's still neural network. You use big data analytics to help them analyze their data to give them some maybe some, let's say, estimation, prediction, or early warnings, or classification, event classification. This kind of thing utilities are more acceptable to this kind of data analytics instead of using AI to do the real control in the system.
Great.
That's just my opinion, okay? Maybe change in the future, but that's what's its
I think you're right. I think the utilities are very conservative. We want to caution the approaches to make sure any changes, without
yes.
affecting the infrastructure. I think we are almost run out of time,
Yeah.
and one last question, because we have graduate students and postdocs are listening. And
Mm.
what is your advice as people want to look into this type of area for future as they work on new models? Anything that you're want to give a piece of advice as you wrap up this webinar?
Yeah, so I would like to say that I really admire and respect all this theoretical research. But if you are in power engineering discipline, I would strongly recommend talking to the utility industry, understand their real problems, making sure that your assumptions in the algorithm development and the model development are realistic in practice. You can't make some assumptions that are unrealistic to the utility industry that will make your algorithm, just purely mathematical practice. You don't want to do that, right? Because we are engineers. Yeah.
Good. Thank you so much, Dr. Zhao. I think you will receive a nice plaque from UND and signed by our dean as well, and a letter of appreciation. I appreciate so much time. We look forward to collaborate with you at some point to go work for some proposals. Thank you so much.
Thank you, Prakash, and thank you all for your for listening to this webinar. Thank you so much, and look forward to seeing you in the future.
Thank you.
Thank you. Bye.